this video, I'm going to take a look at an example problem making use of the conservation of energy method for looking at a simple harmonic motion type situation. So the setup for this problem is that we have a thin circular hoop which is hanging on a peg, and if we give this thin hoop some small angular displacement, meaning we push it slightly to the side and then release it, letting it rock back and forth, what would be the natural frequency in relation to the geometry of the hoop itself? So first, kind of setting up a free body diagram, we have this hoop and it has a center of gravity located at its middle, and we're given that it's resting on the peg located at the top. I'm going to label that location O, and we know that that distance to the peg is 1 radius from the center of gravity. Now we're going to displace the peg by some small amount, or displace the hoop I should say, by some small amount such that its center of gravity has moved to some new location, and that movement kind of traces of the center of gravity, traces a circular arc, and the displacement is here represented by the angle theta. So now in this new position, we can define the position of the center of gravity relative to the peg as r cosine theta. So if I use again this angle here, r being the distance from the center of gravity to the peg, then I know that that distance there must be r cosine theta. At the center of gravity, we have the weight of the hoop itself pulling down, and then of course we have it resting on the peg in the location shown. So we're going to take a conservation of energy approach to this problem. So first, I want to think about what's happening as this peg rotates around, or I keep saying peg, as the hoop rotates around the peg located at O. And therefore, I'm going to represent this as a fixed axis rotation, which uses the moment of inertia about point O times the natural frequency squared. And we're using the natural frequency because we know that if this is being released and is free to rotate, then that rotation must be defined by the natural frequency. I'm also going to need to calculate the mass moment of inertia for the hoop, and I'm going to say that because point O is not at the center of gravity, I'm going to use the parallel axis theorem to take the mass moment of inertia at the center of gravity plus the parallel axis theorem term in order to calculate I sub O. Now, for a thin hoop, we can look in a textbook or online and find that the mass moment of inertia is mr squared, and then it turns out that the distance between these 2 points is also r, so if I substitute that in for d, I get mr squared there as well, so I get a net result of 2 mr squared. So coming back to my kinetic energy calculation, I would say this is equal to 1/2 times 2 mr squared times theta dot squared. So I'm substituting in theta dot here for omega in order to make use of this, and the 1/2 and the 2 cancel, so I get mr squared theta dot squared. So that's my kinetic energy. I also need to think about my potential energy. Now, potential energy is basically how does this thing change position? That's the only real potential energy we have. And if we rotate the hoop about the peg, we can see that it's going to lift the center of gravity by some small amount. So we're going to say that the change is due to the change in height, and therefore it's going to be equal to mg times r minus r cosine theta. So because the difference between those two positions relative to the fixed peg is shown there. So pulling r out, I'm going to set this as mgr 1 minus cosine theta. So the total energy then is going to be equal to mr squared theta dot squared plus mgr 1 minus cosine theta. So just like we've done before in the explanation of the conservation of energy method, if we know the total energy, we know that it must be constant or equal to a constant due to the conservation of energy, and therefore we can take the first time derivative of this equation and get it into standard form in order to find the natural frequency. So that's what we're going to do. So the next step is to take the time derivative. So rearranging this equation and taking the time derivative, we end up with 2mr squared theta dot theta double dot for the first term. And I'm making use of the chain rule again here in order to take the derivative of theta, which is itself a function of t. And I'm going to add on to this mgr, and now the derivative here is sine theta theta dot. Derivative of the constant is 0. So I've got some common terms in here. I have an m, an r, and a theta dot that are all common to both terms. So I'm going to pull those out, mr theta dot. And what's left is 2r theta double dot plus g sine theta. So these common terms can be divided out and go into the 0 term on the right-hand side of the equal sign. So with some rearranging now, I get theta double dot plus g over 2r sine theta equals 0. Now, a common approach at this point would be to use the small angle assumption. And for small angles, we would say that sine theta is equal to theta. And the reason we're going to do that is because it gives us an approximation for small angles that gets us into the standard form a little bit easier than doing a full version. So taking that into account, we get theta double dot plus g over 2r theta equals 0. And therefore, once again, this coefficient on theta gives us natural frequency. All right, so we made a couple of assumptions in there. We used the conservation of energy principle in order to arrive at a natural frequency. And this is, again, an approximation, assuming small angles of displacement and making use of that small angle approximation. All right, thanks.